Hello to you all, and thanks for attending today's Klippel Live webinar based on IEC 60268-1. My name is Kent Peterson, and I'm broadcasting from Workwin in Minneapolis and St. Paul, your US-based home for Klippel products. I hope that all is going well in your location and that your COVID-19 cases are continuing to drop, or at the very least, leveling out. We all need to do our part so that we can all go out and listen to some great live music and continue to manufacture and design musical speakers. Lately, drive-in concerts are starting to pop up. Very interesting. People stay in their vehicles, tune into the radio station, and listen in their cars. It's very interesting. And that might be the way of the future for a while. But that brings us to today's webinar. It's very topical. Today we are discussing multi-tone stimuli and the benefits of measuring in that environment. Very close to using music as a stimulus. However, using music as a stimulus will come at a later date. I believe episode 13, stay tuned. That's our version of a cliffhanger right there. But this is a world we're living in where the quality of the speaker is paramount to the listener. So let's get at it. I remind everyone that if you have a question, please use the Q&A portion below, and we will answer your questions as they come if we are able, and of course at the end of the session. As always, let me introduce Dr. Wolfgang Klippel. Good afternoon, sir. I hope you are well, and the session is now yours.
Okay, hello everybody. I will share here the screen with you. A moment, sorry. Okay. Now I'm ready. As usual, I'm starting with a very short overview of our series. So we started with output-based testing and we solved the problem to make good measurements here in my office. And then we came here to the signal distortion section and we selected good measurement techniques. The last time we have spoken about the harmonic distortion, and today we are speaking about intermodulation distortion, and you will see that's also very important. Yeah, that's our topic. Why? Because music is more than a single tone. A single tone is sufficient to measure harmonics. For intermodulation distortion, we need multiple tones. First, we speak very shortly about the physical causes of the intermodulation distortion. Then I reference to the new things from the standard. You will see that the separation of frequency modulation and amplitude modulation is supported by the standard. That's quite important. Testing with the two-tone stimulus, testing with the multi-tone complex, a very nice signal for that purpose. And we speak a lot about the interpretation of the results. And of course, I will do some practical demos on the JBL Bluetooth speaker here. Okay, we are starting with the first poll. Do you evaluate in certain ways intermodulation distortion? If you say no, I'm staying with only harmonics, then press A. But you can, for the other questions, you can also press multiple buttons. If you are listening to music and if you are using a two-tone stimulus or a multi-tone complex, or you have invented some other ways than use here point E. Now it is becoming more and more stable. The winner of our poll is very clearly C with 33% with a two-tone signal. I'm really surprised. Why? Because with a two-tone signal, it is more tricky. You have to select the right tones. But after that comes listening to music, of course. 1/4 of the participants have never done any intermodulation distortion. That's very interesting. I hope you will enjoy the session. And then we have here, of course, the multi-tone complex. I bet this is a very interesting measurement for you. You will like it because it's simple and it gives a lot of information. Okay, that's it. Let's go on. Let's start with an old slide I presented in session number 6. That was frequency. Here's the frequency. time spectrogram, and the black color shows you the intensity of that. And the interesting point, this is here the undistorted music. Here's our bass below or about 100 hertz, and here is the normal audio band with the singer and other things. And here we see just the BL distortion, and here we are generating not much distortion because we had no displacement, no bass signal, but here where the displacement was high, we get a lot of distortion. And we see actually here that they are not only harmonics from the displacement, they are also at higher frequencies, but they require displacement. That's an interesting point. But then they are intermodulating the full audio band, maybe the guitar, the singer, and so on. And that sounds very bad. We are speaking about that. So this is a critical thing. Here we get some interesting interaction between different signal components. So we need displacement. And you will learn that the amplitude modulation distortions are very bad. They are generating some roughness in the sound, especially if we have a very low frequency signal, like in a woofer. So it has a high impact on sound quality. What causes the intermodulation distortion? They are interaction between two signals. So we need two signals, and it is good to have different signals. If we multiply here the same signal, maybe the two filters which are generating from the input signal, from the voltage, more or less the signal, if they are identical, we see everything with harmonic distortion. But if the two filters are different, then they are generating different state variables, and they are multiplied here with each other and generating strange interactions. Here you see different nonlinearities. Here in red, the force factor nonlinearity, the inductance, and time delay nonlinearity. That's more or less a Doppler effect. For instance, that happens if you have a full band speaker and the speaker produces displacement, also in this direction, and at the same time high frequency signals, then more or less the positioning of the cone changes the distance to the microphone or to your ear. And by changing the distance between the two things, you get varying time delay and intermodulation distortion. What is interesting that for instance, the force factor multiplies current with displacement, which is completely different signals. Displacement only at low frequencies generated by a low pass filter, and the current is more or less generated by a band stop filter at the resonance frequency. Then we have damping effects where the velocity is multiplied with displacement, and then inductance, we are multiplying current also with displacement. What is interesting that those distortions where the signals are different or very different, that you might see not much THD. Here, for instance, if from the BL, if you measure the THD, if the displacement goes down, you have no distortion. The same here. Also here for the inductance, if the displacement goes away, the violin is playing the guitar, also not a bass guitar, lead guitar or something like that, then of course you have no distortion. The same here with Doppler effect. So that means you are making not a comprehensive measurement by measuring THD and harmonics. You need multiple tones, at least two, to get a comprehensive picture. That's why the two-tone measurement technique is so important, and it gives you a lot of information. You can apply immediately to the reproduced stimulus, an FFT, and look to the amplitude spectrum. And you could look also to the phase information. That's a little bit more difficult to interpret. We find later on a better way to see that in the time domain by calculating the envelope. I'm coming back to that. Today, we are not much interested in the harmonics. We have spoken about that on the last session. Yeah, with the intermodulation distortion, we can also calculate some total distortion. Usually, it's only the sum of the second and the third order. To keep it simple, that's according to the IC standard. Yeah, and now what is clear, to have it tidy and well organized, you should use a different positioning of the tones. The more far away the two tones are, the easier it is the interpretation of the spectrum. Here, this bass tone generates the harmonics. We are not interested in that today. And then here we have our high frequency tone, maybe 6, 7 times from the fundamental bass frequency away from that. Then we see here more or less a Christmas tree with the difference tones to lower frequencies and the sum tones to higher frequencies. This distance here between the fundamental and the second order distortion is just identical with the frequency of the bass tone, yeah, or the difference then to the harmonics here. Yeah, and then we get the third order. That's nothing more than, here it comes, that's F2, the carrier frequency or the voice tone frequency, minus 2 times the bass frequency. That's it, very simple. Yeah, here are some definitions according to the IC standard 6268-21. We are looking only to the RMS value of the distortion components, which are around at higher frequencies around the carrier. No? So this is a difference tone. We take the RMS value from that and the sum tones and dividing that by the carrier amplitude. So the voice tone. Usually the distance is so small that you see not much from the loudspeaker response, even from the room response, you see not so much because they are, at least at higher frequencies, very close to the carrier. That's completely different from the harmonics. They are much more away from the fundamental. You could say from the psychoacoustical aspect that they are masked by the fundamental. That's partly true, but not complete, because we are not only detecting distortion in the amplitude domain, we are also going to the time domain and looking to the envelope. That's the point. Okay, let's go on. That are the third order modulation, only a minor difference. The distance is larger, so 2 times the bass tone, or 2 times plus the bass tone to the carrier. That's the only difference. And more or less summing up here, all intermodulation distortion gives the total modulation distortion. More or less the same. Yeah. What is interesting, here we are dividing 2 signals by each other and we end up with a relative measure. That's quite convenient. Why we have not the same problems with the harmonics. It makes actually the results not much more complicated. You will see it. With the harmonics in the last session, it was completely different. If the distance is large between the fundamental and the harmonics, yeah, then you get very complicated curves. Here, it's easier. Yeah, so they are similar to the equivalent input distortion. We can generate that, but it's not necessary. And of course, it's a good idea to measure in the near field to avoid any noise problems. Here you see the result from the second and third order to the total intermodulation distortion. That was here, I'm coming back to that, a voice sweep. We have changed the frequency of the high frequency tone, and we had most likely a constant bass tone. And then you see here at very low frequencies, third order distortions are dominating the total intermodulation distortion. Here, the second order intermodulation distortion. Yeah, and also at very high frequencies here at 4 kilohertz to 10 kilohertz, the second order distortions are dominant. That's sometimes very interesting to see. It tells you immediately whether it is related to a symmetrical nonlinearity, that's the stiffness curve or a BL curve, or to an asymmetric one. Asymmetric one to the second order, symmetric nonlinearities to the third order. Yeah, that's the whole thing here. Now is a big question. How to choose the frequencies from the two tones, and how to change the how to select the frequencies and how to change the frequency of the tones. We have to consider all the combinations, the possible combinations between the two tones here, from 20 hertz to 20 kilohertz for the first one, and here for the second one. If they are identical, it's boring. We are measuring only harmonics. Yeah, they should be different. So, and they should be as different as possible. Then we get some new information which can be not measured with the harmonics. So here you see where it is dark blue, we have completely different frequencies, and we see things which are not visible with the harmonics. And that's here first sweeping the voice tone. We have a constant bass tone here at 20 hertz or higher, and change just the high frequency tone from 200 hertz to 20 kilohertz. Okay. Then we can do the opposite thing. Oh, that's too far. I go back to that here. That's a bass sweep. Here you see we are changing only the bass tone from 20 hertz to 20 kilohertz, usually around the resonance frequency, to change the displacement. That's the idea behind that. But we have a constant high frequency tone, yeah, here at that frequency, usually just in the middle of the audio band, close to 1 kilohertz or something like that. Yeah, what is also interesting is actually sweeping here two tones which have a certain frequency range. That's a combination of the two things. That's also very convenient. And the brown curve here, that's usually happens if you change two tones, but which have a very small difference, usually a constant difference, because then you can set a filter just to the difference frequency between the two frequencies. That's an old technique. That's good for many other things, but for loudspeakers, it is not really a good idea. Why? Because your measurement is so close to the harmonics that you see effectively the same or you get the same information as if you measure just with a single tone and look to the harmonics. So that's a waste of time, I would say. Yeah. Okay, exploit information where the two frequencies are different. That's the message. Now we are coming to the next poll. I asked you a little bit what kind of tone setting you prefer. Here's the 25 persons who have never done any intermodulation distortion. They should say none. And then, of course, you have the option fixed setting of two tones. You have just two tones. You like them very much and you use them always. For instance, if you use, I think the Alma CD with the test tones has something like that. Then sweeping only the bass tone, yeah, and having a fixed high frequency tone, sweeping the voice tone, but having a fixed bass tone, and here sweeping the ratio of the two tones and other ideas. There are plenty of opportunities, but no one so far has used other. So, most of the people, yeah, they have never tried that game using or changing the frequencies. The winner from the intermodulation two-tone measurement engineers or something like that is D, using the sweep tone. I like that. I also think that this provides the most interesting information, that are 25%. Then we have some with a fixed tone setting. That's fine, that's good. Sweeping with a bass tone, that tells you what activates, generates here's a distortion. It's usually displacement, but sometimes it's current, or maybe also some sound pressure things. Yeah, and then this is a combination. There are also some people. That's good. Okay, let's go on. Now, let's make it very simple. What is the simplest setup? What you can always generate? You have maybe in your lab two sinusoidal sweep generators. Get some old ones and connect them via two resistances to sum up the signal and feed this into the amplifier, and then you can already play with that. So you can do here, or we are doing first a bass sweep technique. We are going here around the resonance frequency, half the resonance frequency to twice or a little bit higher. And we are keeping enough distance to the high frequency tone. That's it, yeah? So, and then you are looking, or you are listening. It's a very nice, very sensitive listening test or perceptual test. And you can, of course, measure the second and third order distortion or look to the envelope and something like that. We are coming to that. Yeah, if you're using the relative matrix for intermodulation distortion as provided by the IC standard, and as we have discussed that, then you get here maybe different curves depending on the bass tone. Yeah, here's our resonance frequency, and you see the distortions are becoming smaller at higher frequencies. Then the interesting result is, you have to believe that here we have not the time to telling you the physical background, but you are almost blind for KMS distortion. Why at higher frequencies? Here the voice tone is not involved. Also, that means that, you know, two signals have to be multiplied, and this component here is too small. Yeah, from the inductance, we get a lot of distortion as long as we have enough displacement in X, because it's very simple. Inductance depends on X, so we need that, and then we get 30% intermodulation distortion. But they are at higher frequencies, they are very close to our voice tone, maybe here 1 kilohertz. Yeah, BL is almost the same, but the inductance, depending on I, looks different. Here we get a lot of intermodulation distortion at very low frequencies, at highs, but not at the resonance frequency. It's very simple. It's generated by the current I, and here we have a high impedance, electrical impedance from our loudspeaker, and the transducer sucks not much current. Yeah, and this inductance needs a current. It depends on the current, and it multiplies again the L from I with the current to generate the magnetic flux. Yeah, Doppler needs also displacement, and cone vibration. Yeah, that needs also here our bass signal to generate some intermodulation distortion. You see the green curve is very dominant in all the nonlinearities which are depending on X, yeah, and it's falling after the resonance frequency. Yeah, and now let's come to our first demo. I have to switch. I'm using here the Klippel analyzer system on the Bluetooth speaker. Maybe we can switch on our camera. And we are using the 3D distortion measurement module, the DIS, and I'm switching over here to, oh, I have too much open here. Okay, we are in the part 9, intermodulation distortion. Andrew, is this clearly visible here, my screen? Is this good enough from the quality, or do I need the lens, the magnifying lens? Yeah. Let's start with the first measurement. This is really important. Maybe I switch it on. So here you see, here's my collection of measurements that we are in the first DIS measurement, and I would like to make a bass sweep. That means I'm changing here with frequency 1, my frequency from 70 Hertz to 400 Hertz. but I keep the second tone at a constant frequency of 2 kilohertz. Yeah, but it's so unpleasant to have the same level to the two signals. That's why I have attenuated the high frequency tone by 12 dB. It's not so loud. It will not change the distortion. Why? Because the bass tone here in this case will activate mostly displacement depending distortion, and this goes to the maximal voltage here of 170 millivolt. That is Umax here according to the standard. So this is a critical thing. The bass tone will activate the nonlinearities. You see it. Yeah, that's it. I can just start the measurement. I have to switch on. I'm doing here a near field measurement. You see it. I'm switching now on the JBL Bluetooth speaker and can start my measurement here. So I hope everything. Here you see on the left side, how is the progress? Sorry, I have data and I have to press OK and to accept the warning that I'm deleting the old data. And here you see the progress of the measurement. Yeah, okay. That is, I'm switching off here now. The lens that is too much here. Okay. We don't need that here. And now let's have first a view on the numerical results. That are the relative second order intermodulation distortion generated here from the bass tone around the high frequency tone. No? What is really interesting? It is rising. It has a maximum, then a dip, and then it's rising again, and then it goes down. It's very simple to explain. That's an active system. Here's a high pass filter in it, and not much low frequency signals goes to the speaker. Then we have here the first dip, I have to say, that has a passive radiator in it. And here we have not much coil movement of our transducer in it. But this envelope here is more or less, say, the vibration or related to the displacement of the transducer and the resonance frequency. So somewhere here is the resonance frequency of the transducer. Yeah, at higher frequencies, far away from the resonance frequency, we have not much displacement. That's why the distortion goes down. But look to that. We get here 11% distortion here at the maximum at higher frequencies. Now we should have a look here, or maybe I'm measuring just at this level here. That's 200 Hertz. I can do it quite simple by making a single point measurement and selecting here just 230 Hertz and start the measurement. So that was a very, very short measurement. Now I'm making this large. And here you see the results. That's just our bass tone, voice tone. That are the harmonics from the bass tone. Here are the harmonics from the voice tone. You see you see nothing there in the noise. But look to the intermodulation distortion here. That's now the distortion. That are the second sum difference, third difference, third sum. Yeah, and here it becomes difficult. That's also a harmonic, and here's also other intermodulation distortion, but they are critical. And here you see we have less than almost 20 dB difference. That's here factor 10. Yeah, so that means we are about 11% here. With the third order distortion, it's much less. They are only here 3% distortion. Okay, now here's another interesting thing. Now I can make here a stepped amplitude measurement. I'm stepping in. Now let's switch it on again. I'm stepping in. They said no magnifying glass is better. Okay, thanks. here you see 3 measurement points. They are spaced actually in 6 dB steps. And in the middle, we are just at the Umax defined from the previous measurement, as 170 millivolts, but we are overdriving the loudspeaker in the last step by 6 dB. This is our ship outside, so we have some steamships here on the river, and that was not a measurement. Okay, and we are also half of the maximal voltage. We are starting with that here at 85 millivolt. Yeah, but same frequency setting. I start that. I stopped this here for a moment. Maybe you found out that here for the lower, also minus 6 dB, it sounds quite smooth and acceptable. And then it becomes worse, and at the maximal voltage, it sounds rough. That's a typical characteristic of the intermodulation distortion. Now listen to that, I hope. Now we are coming up here to 16% and 7% in the third order distortion. So it's quite a lot, no? Yeah, but you can play at home with that. So it's quite simple, and we are saving the time. I'm jumping back to the presentation. But Ken, do we have any questions or some urgent questions?
Your timing is impeccable. So one we get often is a simple one. How much IMD is at the point where things are sounding bad, both in percentage and in decibel?
That depends on the signal. With a two-tone signal, you can detect it 1%. I can easily detect 1% intermodulation distortion in a blind test. That means with music, I would say that 10% distortion are detectable by good engineers who are experienced with that. Or if you know how intermodulation distortion sound, then you are much more sensitive for that.
10% is their threshold.
We should be very careful with the threshold. I'm speaking about this in the section setting meaningful tolerances for signal distortion, section 14. So it really depends on the product and something like that.
Very good.
No? Okay. Other question?
Yeah, this one's a little bit more complicated. For proper intermodulation distortion, is it correct that the level of the difference should be the same as the level of the sum, or equal to the symmetry requirement, or in which way is a non-symmetry allowed?
Or I should ask the question. He assumes, or do you assume, the difference of the level of the summed and difference tones? I assume he means that. Correct?
I believe so, yeah.
Then the right answer is, think about this, we have not only one nonlinearity, we have multiple nonlinearities, they overlay, and they are generating different position of the two tones. If you have usually only one nonlinearity, then they are identical. One exception is the inductance has after that a differentiator, and then he is boosting everything.
Right. And finally, do you see the non-symmetry because of the frequency response is not linear or flat?
Symmetry, I mean now only the symmetry here in the spectrum. Here you see, here we have a very asymmetric, I should be very careful, the two tones are too close. But if here the sum tones are much higher than the difference tone, I have spoken about this symmetry, not the symmetry of the nonlinearities. With the nonlinearity symmetry, it's quite simple. If the BL curve is asymmetric, you get second order distortion. If it is a symmetrical decay, you get third order.
Very good. Thank you.
Okay. Now let's go on. That's now the voice sweep. It's more interesting. You see more results. And it's more or less the same setup. You are playing on the other sinusoidal generator. And here we see now more or less the voice tone, the high frequency tone carrier, and we have a very low frequency bass tone. And here are different examples of the curve shape. And now let's speak about the root cause. For the KMS, we see nothing. Why? Because all the KMS is only depending on X. And we have at, say, 7 times the resonance frequency, we have not much displacement. We are at very high frequencies, so that makes not a big difference. Inductance, we see a lot. And why? Because we are multiplying X with current. And as I told you just 1 minute ago, it is rising with frequency due to the differentiation for the self-inductance. That generates this green curve here. That's inductance. BL is independent on the frequency of the voice tone. Everything is intermodulated. A violin, a flute, it doesn't matter. Yeah, yeah. L from I has almost the same curve shape than L from X. Yeah, due to the differentiator. And then comes the Doppler distortion. Because it's related to the distance, to the time delay, we get also, or we see a differentiator in it. So that's identical with the green curve. And finally, we have the cone vibration. So that depends here on the modal resonances. We see some distinct peaks in that. So that's quite typical. No? Yeah, and now it's time for doing that. I'm switching over to the sweep measurement. This is this guy here. Okay, we don't need the lens. The point is, this frequency is fixed here in our setup in the property page. So I have to use that now for the bass tone. I selected here 100 Hertz. And I used F1 now for the voice tone. That's here F1. And I'm going from 700 Hertz, that's seven times away from the bass tone. That's good to separate them, up to 7 kilohertz. Yeah, and this is already the measurement. We can save the time. It sounds more or less similar like the last measurement, but the interesting point is that at this point, at 4 kilohertz, we get here actually 16% second order distortion. We get only 4% here in the third. That means there's an asymmetry somewhere in the system. And of course, we get enough displacement here from the bass tone. But here's another mechanical mechanism in the diaphragm, in the cone. It's a modal resonance here. Maybe this is the surround resonance, which generates here this intermodulation distortion of 16%. No, but we can make it quite short. We are just listening here to 4 kilohertz. I'm selecting here 4 kilohertz, and then you can listen to that. Yeah, here you see. I'm zooming into that. Here's a second order distortion. Yeah, those one here, they are as a 20 dB below the fundamental. From the harmonics, everything is here very, very small. Yeah, the intermodulation distortions are critical. Okay, the interesting point is we get the same peak also in the third order. Here it is relatively small. Yeah, it's about 2%. That's perfect. So the third order, the BL decay is not a problem here. It's an asymmetry in the BL curve. We found it already with some harmonic measurement. Yeah, and now comes, if I'm doing again our voltage stepping here with minus 60 dB, 0 and 60 dB, I get a similar result. And you see also that the waveform here looks a little bit strange. That means the envelope here is much larger than at this position here. That goes or is an indication about the amplitude modulation distortion, which is our next topic. Okay. Yeah, what is also interesting, at 0 dB, at Umax, we are still at reasonable, that are here the purple curves, pink curves, we are almost at reasonable level. Overdriving the loudspeaker, we get significant more distortion. This is more or less not protected by the DSP here. Okay, do you have any questions to the voice tone measurement?
Well, yeah, well, we can knock this question out of the way. This is pertinent and interesting to me too. Can this technique also be used or applied to compression drivers?
Absolutely.
Or are there dominant distortion components of different origins?
Actually, very much. I worked a lot when I spent some time with John Vanderkoy and Stanley Lipschitz here in Waterloo. I worked a lot with the two-tone measurements, actually, and compression drivers. And he has not an anechoic room. I made it in his office. Very good JBL drivers with 100 watt input, 50 watt output. I started working on that usually at 3 o'clock in the morning. And at 5 o'clock, the first guy came. And when he entered the whole facility, he was already shocked about the signal and the loudness and so on. And finally, he found my lab and he, he was quite surprised. You see, you find an AS paper about that, modeling distortion in horn compression drivers. Please read that. That's quite interesting.
Very good, thank you.
Okay, let's go on. Now let's think a little bit about the phase. I know nobody will look to the phase. It's also hard for me, but if you are going back to the time domain, taking the amplitude and the phase, in inverse FFT, you are back in the time domain, then you see interesting things. And actually, a good idea is to make an envelope calculation from more or less the carrier. He is modulated if we have amplitude modulation, and he is not modulated in amplitude if we have phase or frequency modulation. So this is our topic now. And here you see actually the time signal from the microphone. We have a very low bass tone, far below the resonance frequency, and the voice tone is a high frequency thing here filling the blue lines. And you see some artifacts or some symptom from the bass tone that generates the displacement and moves the coil actually from the rest position, where we get a lot of output from the high frequency tone, outwards, where of course the high frequency tone has less sensitivity and less output, and then it comes in again, and then it goes to the other side. No? And if we look to the normal fundamental, then we see the mean value. We don't see the fluctuation of the envelope. But the IC standard and our measurement system also provides the value from the peak value of the envelope and from the minimum here, from the valley, from the dip, and you see it very soon. No? So that's amplitude modulation. So the high frequency amplitude changes with the bass tone. This is one cycle here from the measurement. Yeah. Oh, I forgot to animate that. Here you see if we are outside on the left and right side, we are here in the valleys, in the bottom. Phase modulation caused by the Doppler looks completely different. If you look very careful, then you see that the amplitude of the high frequency signal is always constant here, Yeah, it is only, the bass tone is only overlaid, added to that. Yeah, so we have no amplitude modulation. But if we are looking very to the details in the time domain, then we see that with the Doppler, sometimes the signal arrives a little bit earlier at the microphone and a little bit later. That depends on the distance between cone and microphone. That's it. Yeah, and if you look to the amplitude spectrum, you will see actually no difference between amplitude and phase modulation. You see only the amplitude. And the modulation is actually only caused that you have not only the fundamental carrier, you get some additional components. That's it. But if you look to the phase, then you see a dramatic difference. Here the two, or the bass tone is in phase with the voice tone. So that means they are rotating in this direction, and the two vectors are identical with F2 at a certain position, or here, you can imagine. And what happens now? Now with controversial rotation of the two vectors, here this movement to the left and right side is cancelled. That means only in the direction of the carrier, we are increasing the amplitude or we are reducing the amplitude. That's it. Yeah, so we have a variation of the envelope. That's amplitude modulation distortion. Now, if the phase shift is 90 degrees between the two, the bass tone and the voice tone, then we get a completely different behavior. We are going with our vectors a little bit into the future or into the past. And that's why we are arriving earlier or later at the microphone, and that are phase modulation distortion. Yeah. Here you see how it is animated. So this is the sum of the two vectors that are frequency modulation or phase modulation. Yeah, we have a special session about the audibility of distortion, but here only the motivation why this modulation measurement is important. Think about the most critical situation. Select a very low frequency bass tone. Here for the Bluetooth speaker, 150 Hertz is not really low. The roughness sensation is not very distinct, but it's audible. It goes up to 300, 200 Hertz. But at 30 Hertz, it's dramatic. So that means this problem is for subwoofers very important. And then select any high frequency tone, 500 Hertz, 200 Hertz, something like that. And what happens? Amplitude modulation distortion are clearly audible at 3%, 1%. And you hear it not as a spectrum, you hear it as roughness, something like that. So, and if you have Doppler distortion of the same level or some other phase modulation distortion, then you have to play 30% to have the same impression. So the audibility threshold is 10 times higher. So Doppler is usually not critical. Yeah, here in the book from Zwicker, you find some measurement details. I'm coming back to that on the 12th of August. Okay, now I keep it very short. The IC standard provides some nice metrics to measure really the envelope. So it derives that from signal processing, calculates the mean envelope. That's more or less the typical fundamental. But we can also calculate the variance of the envelope. And this is more or less an RMS variance of the envelope, and referring that to the total mean value from the high frequency carrier. That is our amplitude modulation distortion. Very nice measure. And here you see what happens. That is here more or less the envelope signal. The blue one is a mean value, corresponds to the normal fundamental from the carrier. And here you see the top value if we are just at the maximum, and here the mean if we are in a valley. So yeah, here we are more or less in the highest BL. That's, by the way, a BL problem. Here we are in the BL maximum. Here we are in the BL minimum here here. This is a different problem. That's a surround nonlinearity. Okay. Yeah, also cone boundary condition mode from the surround, and here's cone geometry, and everything is force factor. Okay. And the good thing is we can compare the amount of amplitude modulation distortion here in red directly with the total intermodulation distortion. And usually you will see that at lower frequencies, everything is amplitude modulated, and only at higher frequencies, we get a significant difference. That's usually Doppler. Yeah? That are Doppler distortion. Okay, now it's time for a very short inspection of our measured data. I did it already. Here you see it. We are starting, here you have seen already those numbers. Here you see the normal fundamental from our high frequency tone. And here you see the top value. And now I'm zooming in a little bit into that. That's a little bit higher, let's say 1 dB higher. And here for the bottom value, here we are 2 dB smaller. So, and I measured here is on the in dB in percentage. Here we see again our maximum. I make it very large. That is the contribution from the AM. That's very close to the total distortion, but not at higher frequencies. That comes here from Doppler distortion, no? In the small driver. Yeah, and here at 4 kilohertz, where most likely the surround generates some problem, then you see our high frequency tone is twice as high as here. And that's as second order distortion that comes from the surround. So the dominant distortion is this here, second order. About here, if I increase the level, about 30%. Okay, but all that is not visible in the amplitude spectrum. Then it looks here relatively boring. Oh, do I have any questions to the AM distortion?
Not right now. I think we can proceed.
Okay, very good. Yeah, that are the two-tone measurement, and that was the complicated stuff today. So what is complicated? Not the generation. You need two sinusoidal generators. You can easily separate the distortion from the noise. You have seen we have 60 dB signal-to-noise ratio. It's easy to interpret. It is very good for loudspeaker diagnostics in R&D. You learn a lot if you look to that. It's simple to do, so it's educational. By the way, there's a paper here, Loudspeaker Nonlinearities, where I discuss this in greater detail. It is also the most sensitive stimulus for listening tests. So if you really would like to see your surround mode problems and intermodulation generated by the surround, do it. By the way, the surround is maybe one of the biggest nonlinearity at the moment. Why? Because, or the biggest problem. Why? Because the other one, at the moment, we can easily compensate that with the KCS here with our mirror filter, but with the surround, it is more tricky. And it is a very challenging problem. Think about, you would like to generate enough displacement for the bass, and the same surround is involved with a high frequency modal vibration. So the mode shape is totally changed, and that's why you get easily 20, 30, 40% intermodulation distortion. Solution: don't or operate your woofer below the surround resonance. That means usually 1 kilohertz or something like that. Then the performance of the woofer is usually much better. Okay, disadvantage: you have to find the right frequencies and select them carefully. That's why the multi-tone measurement is so convenient. We are using a lot of tones, and it doesn't matter where the tones are, but it's a sparse spectrum. That means not all the tones not all the frequencies are excited. That simplifies the spectral analysis. We can separate the fundamental components with amplitude and phase from the remaining stuff, harmonic distortion, intermodulation distortion, and noise. Yeah, here you see how it works. This is our sparse multitone spectrum that appears here as green fundamental lines. And then we see below that usually everything is filled. We see the intermodulation distortion, and maybe we can also separate the noise from that by an additional measurement at the beginning without stimulus. What is that here? That's just a fingerprint. We have to say it. Nobody knows. It makes not much sense to find out who is generating component in the fundamental. So that means, is this a harmonic? Is this a difference tone component, some tone component? It doesn't matter. It's a fingerprint, but it's a very meaningful fingerprint. Why? With the stimulus here, you can simulate a steady state music signal. It sounds anyway like an organ tone. It could be also an organ tone or something else. So quite convenient. Next, Paul, do you use this technique for distortion measurement, also a multitone stimulus testing? Please say yes and no. Let's wait. It's astonishing that we have 75% who say no. Why? Because in the literature, there's many have recommended and used that and recommend that for testing. But we have still 25%. That's good. No? Okay. What is different to a chirp? Here you see a chirp signal. If you just look to the amplitude spectrum, maybe if you fill all the lines, yeah, it looks very similar. No? You can, of course, in a multitone signal, fill all the lines in the FFT, in the excitation, and later on in the analysis, you can make the measurement time larger, then you get a higher resolution and can look what is between the lines. So they are in the amplitude spectrum, they are very similar, but not in the phase. In the phase, you see that in a chirp, with the frequency, the phase is changing dramatically with the frequency. And what means that? That's generated in the time domain. We have at one frequency only, or at one time only one frequency. And that's coded more or less in the phase spectrum. Yeah. And what happens with a multitone complex? We may have the same amplitude spectrum, but now the phases are scrambled. So we have different phase shifts. And in the time domain, we cannot say that each frequency comes with a logarithmic time frequency mapping. No, they are interacting with each other. We have at the same time multiple frequencies active. Okay, yeah, how to make reproducible tests? Then we have to define the properties of the multitone signal. That's done here in the IC standards. It's quite important to promote a little bit the multitone testing. So that means that we have some comparability from different measurement instrument providers like Head Acoustic, Listen, and Klippel, and something like that. It should be easy to generate by software implementation, and you can modify the stimulus, you can change the bandwidth, the resolution, and so on. So, okay, you have here your amplitude information, frequency dependent, no? And then, more important, that's a critical point, we have to define the phase, because the phase determines how much nonlinear distortion are generated. How is the interaction between displacement and the high frequency signals? And we solved that by using a pseudo-random generator for selecting the right phase here. And of course, here, that's just the definition of the logarithmic spacing of the different tones. So it's similar to the chirp, but it's sparse, and the phase responses are random. That's the main idea. pseudo-random. You can nicely generate that. And how is with the interpretation? With the total harmonic distortion, we learned that we are looking, if we are seeing the THD, we are not looking to the spectrum. No, the spectrum was processed, and we are collecting for a certain excitation frequency. That's a frequency of the fundamental component. We are collecting the energy of all higher order harmonics. So that was with the THD. With a multitone, it's different. Now, the excitation frequency explains the position of the fundamental. And the multitone distortion, they are now all kinds of harmonic intermodulation distortion. That's the fingerprint. We don't know what is the exciting frequency. So that's more or less the view on a spectrum. So that's the instantaneous spectrum. And the distance here explains directly more or less the psychoacoustical masking of the distortion. So this is here actually quite interesting. Yeah, but the spectral amplitude masking is not the only thing. We have to go into the time domain to explain really the roughness sensation. That means this is much more important, the amplitude modulation distortion. Okay, now just here the different curves. The blue curve is the THD. Very high values, usually almost 90%. But usually about 1%, yeah, at 500 hertz. Here. That's minus 40 dB or even more. That's about 1%. So sorry, that was a single tone measured just the THD. It should sound not so bad because we have only 1% distortion. And now the same with the same voltage applied to a two-tone signal. Yeah, so almost the same total amplitude, 15 volts for the bass tone, making a lot of displacement, and only 3 volt for the voice tone, and that then sounds something like that. That was from the THD. And here now comes the two-tone signal. You hear very clearly the intermodulation distortion, and sometimes we have here very huge intermodulation distortion. Driving the loudspeaker hard, we get it. So that's here almost 100%. Sometimes intermodulation products are higher than the carrier because the energy from the carrier goes to the intermodulation sidebands. That's why we are a little bit higher here. Yeah, and with a multitone, we are spreading here the distortion or the energy to all lines. That's why we have usually less. That's the multitone distortion, but what you immediately see is a relatively flat curve, yeah? And you see some peaks here from some modal resonances and so on. So, okay, now let's interpret that. That's not the excitation frequency, that's the spectral component from the distortion here. Yeah, stiffness at very, very low frequencies, BL distortion. But we may see something from the harmonics and from the GMS distortion here in this region. From the BL, everything is affected. So here this flat line comes mostly from the BL. Inductance, it's rising at higher frequencies, but usually the BL are stronger. Then here from the nonlinear damping, that's close to the resonance frequency. Inductance is also rising, and Doppler effect is also rising, and cone vibration comes here with the peaks. Okay, that's it. And now, actually, that is a byproduct from our Klippel controlled sound research. We are using very much a multitone stimulus for that. And here you see the total distortion from a woofer. And if we have the nonlinear parameters, we can actually explain what comes from the stiffness, what comes from the BL. That's usually everything. So at all frequencies, there's a contribution. It's a flat curve. This is here out of band. The fundamentals stopped here. And what you see here, that are usually harmonics. They are usually at 1%. But intermodulation distortion, yeah, between the tones, they are usually 20 dB, easily higher, no? Or sometimes more, 30. Yeah, the inductance L from X is quite high, and the L from I. L from I is actually the main cause of the distortion, of the out-of-band distortion, because we need no displacement, we need only current. And then you come to your 1% value, which is usually printed in the spec sheets of loudspeakers. But in reality, the other nonlinearities make 10 times more. Yeah, the same for a micro speaker. This is the total distortion, that's the out-of-band distortion. Now we are here at 1 kilohertz. No, the resonance frequency here is about 700 hertz. That's BL, constant, frequency independent. Stiff, then comes, that's RMS, nonlinear damping. And this is here stiffness, very dominant at low frequencies, falling very steeply at higher frequencies. And finally, we get the inductance distortion, which are negligible, but usually rising with frequency. So quite simple. Yeah, let's summarize multi-tone distortion measurement. What are the advantages? We consider intermodulation distortion. It's audio-like. You can nicely separate noise and distortion. It is very, very fast measurement. You are spending maybe 500 milliseconds, half a second, and you get a lot of information. Yeah, it's perfect for end-of-line testing. What are the disadvantages? Amplitude and phase have to be defined. If you think about that, if all the tones are in phase, you get a huge impulse, high displacement, actually some intermodulation distortion, but it's a very critical, very dangerous stimulus. If you have from the phase here the frequency time mapping, the logarithmic, you get a chirp more or less. So it depends highly on the properties of the phase. That's why we have defined that. You cannot separate odd order and even order distortion. Not if you have more than, I would say, 5-10 lines, forget it. Yeah, it doesn't, and that means you don't see the asymmetry or the symmetrical properties from the nonlinearities. That's related with the odd and even order distortion components. And we cannot separate harmonics and intermodulation distortion. And the fundamental is also distorted. But it's a very powerful test. So I would like to illustrate that very shortly here on in the software. So I close that, and now we are on the multi-tone testing. Is the camera switched on? I go back to the say in situ measurement. We use this in the other experiments with a distance of 30 centimeters. I clean up a little bit my screen. And actually we have actually provided a reference data here from the near field scanning. And now I have to make actually, I show again the calibration, but it goes so quickly. I have to make one measurement. Oh, it's switched off. Okay, and now let's do that. So okay, that's the measurement at this point. And now I did this already. I remove this. Sorry. I remove here this measurement. I don't need that. And now in this in situ calculation, I can, with this new in situ measurement, measured here, which sounds a little bit ugly, distorted by the room reflections, I can generate with the reference data from the near field scanner by pressing the button a new room correction curve. It's done. And now here you see our result looks quite smooth and flat. Everything is fine. And I can now grab this curve here. This curve, room correction curve, depends on the position of the microphone. If I change the microphone, and I did, that's why I have to redo the measurement, and now I go here to the M-tone measurement. Yeah, you have seen it already in the previous section, and I import that here under room correction curve from the clipboard. Now it's in that. I lose the alt data, and now I can press here the button. I'm doing the measurement here at the at Umax 170 millivolt. Here's the black stuff. That was actually I did it during the noise floor measurement, so that's me here. You know? But the main measurement here was not corrupted. If you like, I can repeat this. It's fast. Now you see we have here 80 dB signal to noise ratio. That's good. That are the fundamentals. I make it a little bit larger. Yeah, that's the noise floor. And that are the distortions plus noise. But we know here are the distortion and the noise are almost at the same level. If I switch from noise floor to noise and distortion, you see it's identical. But this here has a very good signal to noise ratio of at least 20-30 dB. But we have not much distortion. You see it here, that's proposed by Alex Boschwillow. That's more or less an energetic measure of the distortion component. So they are smoothed here and averaged a little bit. But maybe I should zoom into that. That's here maybe 1 octave. Make it quite large. Then you that's here the noise, and that are our distortions, and this is here the smooth distortion measure. It's not at the peaks, it's just in the middle here. And they are relatively high, close to the fundamental. But not this distance here is really important, because really in the amplitude spectrum, this perspective is like evaluating Doppler distortion. That's most likely masked, but not in the time domain where we see the fluctuations. Yeah, that is here the Boschwillow curve, I could say, the mean THD curve. And what we really see, it covers, or it's almost constant over a wide frequency range from 200 Hertz up to 400 kilohertz. And here it falls down. Okay, and if you are comparing that, and even at lower frequencies, we have lower distortions. If we are comparing this with the harmonics here in the last measurement, no, that was equivalent, that one here, from the last session. We had about 100% at very low frequencies, and then we got here a falling line, and we had almost nothing here at higher frequencies. That's not complete correct. And with this module, we find here 12% distortion. So that gives you a much more, say, typical picture how the distortions are in the music signal. Okay, and now let's make a very short, or we can just look to that. I skip the measurement. Here you see the search for the maximal distortion. I started here at 100 millivolt. I stopped at 400 millivolt. Some protection system is active here and something like that, but we get almost the same curve shape. So that means the protection system has generated here the compression of 7 dB. Yeah, but we ended up with almost the same amount of distortion. From the multitone distortion, it's minus 30 dB. So that's quite good. That's but it's not comparable with the 10% value with the two-tone. We have a different stimulus, so that's a completely different metric. Here, usually -30 is already, can be already critical. That depends in the time domain on the amplitude modulation distortion. Okay, do you have any questions to that?
Not specifically. There's more of a general question.
Yes.
And forgive me to the questioner. I'll do my best to interpret this. Here's a general question. For all of the spectrum graphics, how does the software obtain the real magnitude after it applies the FFT to the impulse response or other type of signals?
Usually, if we have the spectrum, we are staying in the spectrum. We are maybe from the harmonics or from some other metrics, we are comparing the distortion with the fundamental lines, because the fundamental lines are good and the distortion are bad, and we are looking to the relationship. Do you mean that? But
yeah, I think so. It's hard for me to obtain the, what the questioner is asking specifically, but I think you're at the heart of it.
Yeah, I say again, the most important thing, if you compare THD with multitone measurement, that's a spectrum. This is the fundamental output, we like it. That's the intermodulation harmonic distortion, which are not good. And this is the noise. And they are competing with each other. What we do not see is what happens in the time domain with the roughness. And the multitone testing is not good for separating amplitude modulation distortion from phase modulation distortion, because we have not the right information for that. Okay, let's go now to the multitone. Oh, I skipped via the discussion, but now it's time for some other questions, if we have some.
Send them in, people. Here's a question, and I think we're probably going to address this down the road a little bit. In comparing devices, 60268 has a lot of ways to evaluate distortion in devices. Is there going to be a point at which we can understand how we can receive a good comparison between two different devices and trim the amount of measurements we look at?
By the way, I will speak exactly about this topic after my break. So that means on the 29th of July, benchmarking of audio products under standard conditions. Right. So that means at that point, I try to select the most important things. I imagine you have no time, you have only 15 minutes for doing the measurement, and you would like to get the most important information and not overseen something. So this is actually in session benchmarking of audio product number 12. And later on comes what is really important, how to set limits, distortion limits. That's much more critical.
Right. It's a very comprehensive standard.
No. Right. Okay. Do we have some other interesting? I hope it is enough for today.
I think it must have been a completely understandable session, because I think we cleared up all the questions at this point.
Okay, now let's do the summary. To make it very simple, intermodulation distortion are valuable from the diagnostic point, yeah, and they are giving additional information which are not in the harmonics. That's why we have to do it, yeah. For instance, intermodulation distortion is the only valid or practical symptom for L from X nonlinearity, and that's directly related to shorting rings. No? So if you have some questions, shall we spend money on shorting rings or not? You should do some intermodulation measurements. With a multitone measurement, in some aspects, you get also the same information like from the THD, and even more. So that means if you have only time at end of line testing for one test, and you are interested in regular distortion, not rub and bus, then a multitone would be sufficient. But in the next session, you will learn that we need the chirp for rub and bus testing very much. So that means the two most important tests are a chirp for rub and bass and a multitone for all the regular distortion harmonics and intermodulation distortion. That's more or less one important thing. So it shows the impact of the program material. You can shape the fundamental in the stimulus and see whether you get more or less distortion, something like that. It's quite nice. With the two-tone, it's a little bit academic, but it's simpler and you see the even and odd order. So it has also its value, but it needs more time. Yeah, that's it with the summary. And yeah, then I said already we have to speak about rub and bass and other irregular properties. That comes in the next session. It uses the term or introduces the term impulsive distortion, because that's just the main symptom of rub and bass and other abnormal behavior. Yeah, and we speak a little bit why we are generating new special measurement techniques which are described in the standard, which are more sensitive than the human ear. And what we learn from the time frequency analysis, that's quite interesting. And we are going actually into the fine structure of the impulsive distortion. Listen to that and actually doing some tricks to understand the pattern of the fine structure. That's quite interesting. That's the key, by the way, to understand the root cause for rub and bass and other things. Yeah, and this is also part or provided by the IC standard. I think that's it. That's our next session, and then comes a small break. But Kent, you have already an idea for the small break? I'm in vacation, but
yeah. Well, we were thinking if everybody's up for it. I don't know who's still listening, but we were thinking of getting all the other Klippel engineers, Stefan, Christian, and maybe having a Between Two Ferns or an open round table where you could ask whatever questions you want to ask. It might turn into a complete mess, but I think it'd be fun. If you want that, please go ahead and comment now in the chat window or the Q&A window. I think it'd be fun. We can let Wolfgang go on and do some paddling in his canoe, and we can find a time to meet and I don't know, as we say, shoot the shit and have some open questions to the guys at Klippel. And oh yeah, good. Oh, look at it's blowing up. They're liking it. Oh, now we've got to put it together. So okay, that's great. Are you going to take your swim now, Wolfgang? Your evening swim?
No, we have some other things to do tonight. But it would be a good idea. By the way, I'm going not alone canoeing. I take my wife, Miss.
Or well, I would hope so. Okay. Unless she doesn't like canoeing. So,
yes, she likes.
Okay, good. Well, we've got some good responses for that. We'll try to put that together, and we'll get a big Zoom meeting going with the engineers, and maybe we'll just have a cup of coffee or a nice tall beer and discuss some questions. And for that, we'll sign off for today. Thank you, everybody, for showing up as always. Stay safe. Love what you do. Love those around you. And we will see you next week, and we'll put that panel together. Thanks, everybody. Thanks, Wolfgang.
Goodbye.